The modern world depends on electricity. It's not just a luxury we use to power our devices and enjoy our free time. It's not even just the convenience of having light, heating, and cooling in our buildings. Electricity is a crucial resource, especially in urban areas, providing public security, safety, and health, and making possible everything from emergency response to modern medical care in hospitals to even the other utilities we require, like fresh water and sanitation systems. But unlike those other utilities, electricity can't be created, stored, and used at a later time. The instant it's produced, it's used, no matter how far away the producer is from the user. And the infrastructure that makes all this possible is one of humanity's most important and fascinating engineering achievements. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about the power grid. This video is sponsored by NordVPN. Visit nordvpn.com/practicalengineering to get 75% off a 3-year plan. More on that later. Like most people, you probably take the grid for granted. Electrical infrastructure is so ubiquitous, it's easy not to notice that most of our power grid is out in the open for anyone to have a look. I happen to be one of those people who does want to have a look, and hopefully by the end of this video series on electrical infrastructure, you will be too. This video is geared toward North America, but most of the concepts will apply to any other part of the world. And just to give you a sense of scale, there are only 4 distinct electrical grids that service essentially all of North America. You have the 2 big ones, Western and Eastern, and the 2 electrical separatists, Quebec and Texas. Depending on your definition, an electrical grid can be considered one of the world's largest machines. So how does this machine work? The basic function of generating electricity and delivering it to those who need it may seem simple. I can hook up a small generator to a light and boom, power grid. With the cost of solar panels reaching record lows, many are exploring the possibility of generating all the power they need at home and forgoing the grid altogether. But a wide area interconnection, that's the technical term for power grid, offers some serious advantages in exchange for increased complexity. Here's a simplified diagram showing the major components of a typical power grid, and we'll follow the flow of electrical current as it makes its way through each one. We start with generation, where the electricity is produced. There are many types of power plants, each with their own distinct advantages and disadvantages, but they all have one thing in common. They take one kind of energy and convert it into electrical energy. Most power plants are located away from populated areas, so that electricity they create needs to be efficiently transported. That's handled by high voltage transmission lines. At the plant, transformers boost the voltage to minimize losses within these lines as electricity makes its way to the areas that need it. Once it reaches populated areas, transformers then step down the power back to a safer and more practical voltage. This is done at a substation, which also has equipment to regulate the quality of electricity and breakers to isolate potential faults. Some energy customers draw power directly from the transmission lines, but most are served from feeder lines that carry power from the substation. This part of the system is called distribution. From the feeders, smaller transformers step down the voltage to its final level for industrial, commercial, or residential uses before the electricity reaches its final destination. Rather than a constant flow of current in a single direction, called direct current, or DC, the vast majority of the power grid uses alternating current, or AC, where the direction of voltage and current are constantly switching, 60 times per second in North America. The major advantage of AC power is that it's easy to step up or down voltages, a critical part of efficiently and safely moving electricity from producer to consumer. The device that performs this important role, called a transformer, is as simple as a pair of coils next to one another. A varying voltage in one coil induces a voltage in the other coil proportional to the number of turns in each one. If the current doesn't vary, like in direct current, the transformer can't do any transforming. It's helpful to think of the grid as a marketplace. Power producers bring their electricity to the market by connecting to the power grid, and power consumers purchase that electricity for use in their home or business. The economics and politics of the grid are so much more complicated than this, but the important part of the analogy is that in many ways, the power grid is a shared resource. Because of that, it needs organizations to oversee and establish rules about how each participant in the producing, transmitting, and consuming of power may use it. And there are three overarching technical goals that engineers use to design and maintain the power grid. The first one is power quality. Our electrical devices and equipment are designed assuming that the power coming from the grid has certain parameters, mainly that the voltage and frequency are correct and stable. Some devices even count the oscillations in the AC grid power to keep track of time, so it's critical that grid frequency not deviate. Changes in voltage can lead to brownouts or surges that damage connected equipment. One of the benefits of large power grids is electrical inertia. All those huge spinning generators connected together provide momentum that smooths out the ripples and spikes that can occur from equipment faults or quickly changing electrical loads. The next technical goal of the grid is reliability. If, like most people, you take the constant availability of power for granted, that's by design. Much of the grid's complexity comes from how we manage faults and provide redundancy so that you're rarely faced with blackout conditions. It's another inherent benefit of a grid that electricity can be rerouted when a piece of equipment is out of service, whether it was planned or otherwise. The final goal of the power grid is simply that the supply meet the demand. Electricity production and consumption happen on a real-time basis. That means if it's plugged in, the light from the screen you're watching right now was a drop of water in a turbine or a breeze across a windmill just microseconds ago. And by the way, did you call your utility and let them know that you were going to be turning on your computer or phone to watch this video? I'm willing to bet you didn't, which means not only did they have to adjust their production up to match the extra load, but they had to do it immediately without any warning whatsoever. Luckily, having millions of people connected to the same grid smooths out the demand created by individuals, but load following is still a major challenge. For the most part, electrical demand follows a fairly consistent pattern, but factors like extreme weather can make it difficult to forecast. Grid operators balance demand by dispatching generation capacity in real time. The cheapest sources of power are used to fulfill the base load that's more consistent, and higher cost sources are used for peaking when demand exceeds the base. But it's not as simple as flipping on a switch. Large power plants can take hours, days, or even weeks to start up and shut down. Equipment needs to be taken out of service for maintenance. Fuel costs fluctuate. Renewable sources like wind and solar can have massive and unpredictable variations in capacity, providing irregular sloshes of power to the grid. You can see why balancing electricity supply and demand is this fantastically complex job of taking into account all these considerations, some of which are predictable and some of which aren't. That's part of the reason we're trying to make the grid smarter by using software, sensors, and devices capable of communicating with each other. On the supply side, this can allow computers and software to do what they do best: take in and process huge amounts of data to help us make decisions about how to manage the grid. But a smart grid can also help on the demand side as well. Unlike most of the goods we buy, consumers don't have a keen understanding of power, how much we're using, or how much it should cost depending on the time of day or year. A smart grid can take away some of that obfuscation, allowing us to make decisions about how we use electricity in our day-to-day lives. Ultimately, the smart grid can help us use and take care of this huge machine, this shared resource we call the power grid, more effectively and efficiently now and into the future. Just like electricity, internet connectivity is a resource on which we depend more and more. I work on these videos in my spare time, which means I'm connecting to all kinds of sketchy networks wherever I happen to be. That's why I use NordVPN. A lot of people don't realize how vulnerable you can be when connecting to unsecured Wi-Fi networks at coffee shops, airports, convention centers, etc. One stolen password can completely mess up your finances or worse. What I love best about NordVPN is that I don't have to balance inconvenience with the possibility of having my identity stolen or computer exposed to malware, because it's so easy to use. I just load the app, click connect, and it's done. There's no limit on bandwidth, and it works on all my devices. I have insurance on my car in case I get into an accident. I lock the doors on my house in case of an intruder, and I use NordVPN, especially when I'm on public Wi-Fi networks, to protect myself against hackers and malware. If your privacy and security online is important to you, they're offering an awesome discount to fans of the channel. Visit nordvpn.com/practicalengineering or click the link in the description below to get 75% off a 3-year plan. Use promo code PRACTICALENGINEERING to get an extra month free. Thank you for watching, and let me know what you think.